All right, how's it going? Good. Any questions about anything we've talked about so far? Deadlines, whatever else? Are you all aware you have something to do midnight tonight? Go ahead. Yeah.
But with the online question,
Uh-huh.
is there any like final submit thing you have to do, or do you just have?
No, every time you submit submit a problem and you get it right, it updates your score.
Okay,
So if you're done, there's nothing else you need to do.
so you don't need to do anything on Canvas either?
No. Also, the way it usually works is I'm sure there's a way to integrate WebWork to Canvas. I don't know what it is. So I just go into WebWork. I'll go into WebWork sometime tomorrow and just scale your scores out of 10 and drop them into Canvas. So once you've done the thing on WebWork, you're good. I'll handle it from there. Of course. Anything else? One thing I have not said, I think I put this in an announcement, but I feel like when I was an undergrad a long time ago, we kind of looked at deadlines as these non-negotiable things that were set in stone. So, I mean, I set deadlines because I have to, but I understand that this is not your only class. School is not your only obligation. Life happens, things come up. If there's anything, for any reason that you think you can't hit one of the due dates I have, let me know. I almost never say no to people who ask for extensions. If you're asking for them very, very often, we'll probably have a conversation about why that's going on and how I can support. But yeah, if you feel like you're not going to be able to meet something, let me know and I'll work with you. Make sense? But I feel like when I was 20 years old, I was definitely afraid to ask for those things, or whatever age most of you are. So don't be afraid to ask me. I almost always grant them, but yeah, I'm here to support. So we finished 5.5 last time, integration by substitution. We're going to move on to integration by parts today. So again, like we're all more comfortable, I believe, in dealing with derivatives. So let's go that direction first. I have this function here, f of x equals x e to the negative x. How can I find that derivative? What things do I have to think about? Product rule. Product rule. What tells you that the product rule is something you need to pay attention to? X multiplied by e to the negative x. Right. So you have x multiplied by e to the negative x. This is probably not a function you know its derivative off the top of your head like you do with x, like you do with e to the x. But you can basically split this function up into those building blocks multiplied together. So if you do that, how do you make use of the product rule to get to this derivative? Derivative of x times the derivative of e to the negative x. Done. What do we got to do? Do you remember? Go ahead.
Derivative of x times e to the negative x.
Right. So we're going to. So this derivative is going to be equal to this derivative times e to the negative x plus
The derivative.
this times the derivative of this, right? So right, basically what you're doing with the product rule, the way I like to think of it is you have two different functions and the rate of change comes from keeping one of them fixed and letting the other one change by a little bit. Then letting the other one be fixed and let the first function change. And then that sum goes up. That sum is your true rate of change. So, and kind of looking ahead, basically what we're going to be doing today is undoing this process that you've seen before. I just want to make sure this is familiar to people, just in case it's been more than a semester. The product rule of differentiation, the way it's set up. So now we can do this, right? So the derivatives we need are of x, which is 1. And the derivative of e to the negative x, which is negative e to the negative x. Where does that negative coefficient come from? So chain rule. So this is one of those times where whether or not you realize it or whether or not you set it up that way, you're using the chain rule. So if we clean that up a little bit, we get e to the negative x minus x e to the negative x. So going the derivative direction, we okay with that? Any questions here? Okay, so what does it look like when we undo? So the product rule, basically what we're doing is this. We have some function that's actually being treated as two functions multiplied together. We want to take its derivative. So we did a specific example. In general, how does this thing work? It's the derivative of one times the other, and the derivative of the other times the first. That's sum, right? So basically what we're going to do is undo this to try to integrate. So now what I would like to do is basically undo this process. So here's what I'm going to do. I'm going to solve for one of these, either f prime of x gx or fx g prime of x. And kind of take this on faith for now, but I'll explain this in more detail after I work it out. But it doesn't really matter which one of those I do. Any preference? Which one of those should I isolate? All right, sounds good. So if I isolate that, I get f prime of x times g of x equals f of x g prime of x. No. I don't know why this is tripping up today. F of x, g of x, that derivative minus f of x, g prime of x. So all I did was isolate that f prime of x, g of x, the one you asked for, right? So what happens now if I integrate both sides? So this right here, this integral of f prime of x, gx, basically I am going to, basically I can integrate both of these terms. So this f of x, g of x, if I integrate this f of x, g of x, that whole derivative, if I integrate that, what do I get? Right, so fundamental theorem of calculus tells us that those operations are inverses of one another. So that just becomes f of x, g of x, and this becomes minus the integral of f of x, g prime of x. So this right here is essentially the undoing of the product rule. This is what you'll almost always see called the integration by parts. So basically the way this is going to work in practice is I want to integrate this thing, which is probably not doable directly, but I can trade it for this other thing, which hopefully I can't do this integral, but hopefully I can manipulate it so I can integrate this thing, which is hopefully easier. So let's see how that works in practice. Well, I wrote it by hand. I have a head on a slide, but basically this is what I just showed you. I think it's this one here. I actually isolated the other one, but one thing I do want to point out, the product rule is completely symmetrical. I could rename functions f and g as each other, and I have the same exact representation. For those of you who have seen this rule before, you've probably seen this exclusively written in terms of u and v. So instead of calling these functions f of x and g of x, we call them u and v. Call their derivatives du and dv. How are we doing so far? Okay. So here's an integral, the integral of x sine of x dx, that we would like to use integration by parts on. So I want to focus for a bit on this bottom kind of representation just because it's more compact. And it's probably going to be the preferred way that if you think about it, just because there's less array. But the integral of u dv, so basically the integral of one of these functions times the derivative of the other is equal to the product of those functions minus, you know, this other integral where these functions are reversed, v to u. So we've developed it, now let's go ahead and use it. So I know the integral of u dv is equal to uv minus the integral of v du. So this is where we're starting. We want to start with u dv, which means that we have some decisions to make. The function that I'm giving you is x sine of x. That's the thing I want to integrate. That is probably not a thing you know the integral of off the top of your head like you do with like the integral of x. You can probably just give me that. X sine of x, not so much. So here are the decisions we have to make. We have a product. I want to call part of that thing u. I want to call the other part of that thing dv. But kind of like with integration by substitution, after I make a decision for what u is, what was like the first consequence of that in integration by substitution? Right, so if you choose a u, then you don't get to choose what du is. It's a byproduct of whatever you choose for u. Similarly with dv, after I choose what dv is, what's the consequence that results from that? You find v, right? So basically what we're doing here, mechanically speaking, is we're going to split up x sine x into two pieces such that when you multiply them together, it gives you x sine of x. And we're going to integrate one and differentiate the other. So how do we make the decision into which one to integrate, which one to differentiate? Let's just see what your first impulses are. Which one should we choose for you? So the one we're going to take a derivative of. X. And do you know why you want to choose x?
The derivative is 1.
So the derivative is 1, and why is that important? Makes it easier. So and that's typically, not always, but typically what you look for. If there's something I can take a derivative of and make my overall function simpler, that's usually a good place to start. We'll find out right away if that doesn't work, but usually a good place to start. So from there, what does that mean dv is? Sine of x dx, which means v has to be. I heard mumbles and then the word cosine. Negative cosine. Are we sure?
Yeah.
Okay. All right, I agree with this. So we have u du, v, and dv. So now we should be able to follow integration by parts and set this up. So the integral of u dv is equal to uv, which is, oh, go ahead, question?
With the dx, can't it like translate over to the v from dv?
Oh, no, you're right. It would not. So yeah, v is just negative cosine x. Thank you for catching that. All right, so the integral of u dv is equal to uv. In this case, what is my uv? Yeah, so x times negative cosine x. So for now, I'll just keep all these things distinct. X times negative cosine x minus the integral of v du, which is what? Negative cosine x dx. So the way I kind of described what integration by parts is trying to do for you is you're trading in an integral you can't do directly for an integral that hopefully is manageable. Do we think we've done that? Okay. So if we clean this up a little bit, we get negative x cosine x. These become positive. Do I know what the integral of cosine x is? Sine of x, right? So in trading our unmanageable integral in for one that was manageable, we're able to do the one that we kind of avoided. We were able to do the integral indirectly because we couldn't do it directly. So let's recap here. What did we start by doing? We need u, and so we need to start with u, right? What's the consequence of you choosing that u? Derivative. What else is a consequence of choosing that u?
It defines DV.
It defines DV, and then what does DV define? Right, so how many choices do you really get to make in this process? Once you choose X, you're kind of stuck. Which might sound like bad news. I think it's good news because I think it's. If you hit a dead end, you'll be able to see it pretty quick. In this case, the first thing we tried worked. So after we choose U and look at all the stuff that falls out of that, where do we go from there?
Everything right there. Kind of a formula.
Right, so then, yeah, we're essentially filling in that integration by parts. How are we doing so far? You have a question?
Yeah, so how do you know that you're supposed to use by parts rule instead of substitution?
A good question. And this is gonna be a thing that kind of trips you up. So, section 5.5 is all about substitution. This one's all about integration by parts. Before long, I'm gonna make you make that choice. So this is a good time to talk about it. What is integration by substitution useful for?
Inner and outer functions.
Inner and outer functions, what do we call that operation when you have?
Chain rule?
Chain rule, yes, but trying to think of the right way to ask this. Yes, it is chain rule. What is the chain rule useful for? What kinds of things? I mean, you said inner and outer functions. I'm looking for it's a composite function, right? So a composite function by definition is a function that, the output of one of those functions becomes the input to some other function. So lots of ways to combine function. Composition is one of them. Chain rule is good for differentiating those kinds of things. Integration by substitution is good for integrating those kinds of functions. As opposed to integration by parts, what kinds of functions am I using this for? I know we've only done one, but why did we have to use it here? That's a better way to ask it. Right. Right. So multiplication, not of different, of different variable functions, right? So substitution in a nutshell is all about undoing the chain rule and dealing with composite functions. Integration by parts is all about dealing with functions that are not combined, by nesting them like that, but by multiplying two different functions together. I'll give you a couple more kind of tools to hopefully kind of make that a little easier to organize for you, but I think I should do a couple more examples of this first. But that's a tricky thing to kind of get used to, is when do I use this thing? When do I use the other thing? So hold that thought. I'll answer that in a different way in a little bit. All right, the integral of natural log of x. Seems pretty simple. There's not a lot going on there. But do you know what the integral of natural log of x is? Is this something you've ever thought about? So you don't know what it is, and so because of that, we can't really handle this directly. Can we use substitution or integration by parts? Go ahead.
We can say U equals 1 and 1 of x equals v prime equals natural log.
Okay, I think that's a good place to start. Is that legal? Can I say that U equals 1 and dv equals natural log of x dx? So once again, I'll write this thing down. The integral of u dv is equal to uv minus the integral of v du. It is so. There's a couple questions I want to ask. The first one is, does this make sense? First of all, is natural log of x equal to this u times this dv?
Yeah.
Okay, so we could start there, but I think you have a protest.
I said we should switch that on that.
Okay.
Like you should be natural log and EV should be 1.
Okay, so I'm glad this is coming up. Why are you saying we should switch them?
Because we don't know what the derivative is.
Right. Right. So of that choice you get to make for you, you're essentially choosing, all right, I can't integrate this thing, so I'll take a derivative of it because I can do that. But if you call dv natural log of x, then you are requiring yourself to to integrate it, which is the thing we already decided we couldn't do. So what happens if we move them? So natural log of x is equal to u, and dv is equal to dx. So first, is this legal? Does that u times that dv equal the thing I'm trying to integrate? Excellent. So now I get to write down the other consequences of my decision. What is du? 1 over x dx. And v is x. Okay. So now let's see what this did for us. The natural log of x. The integral of the natural log of x dx equals uv, which is x natural log of x minus what?
The integral of x.
Not the integral of x. Also, the integral of x, is that it?
Like one.
X times 1 over x times dx. Simplify inside the integral to get the integral of dx. So we traded the integral we can't do, hopefully for something that we could do. Can we integrate dx? You can, but it might be subtle as to how that happens.
Okay.
It's x, right? So I mean, you can think of it as you integrating 1 with respect to x. Any questions there?
With the du,
Mhm.
the first thing you did.
Mhm.
The derivative of 1 over x is ln x, right?
Other way around. The derivative of natural log of x is 1 over x. Yes. Sound familiar?
Oh, no, yeah.
Okay, okay.
I forgot, like.
That's one of those, I feel like that erodes.
Like some of the little rules like I.
It's like the power rule, we want the power rule to work all the time, and you think that I remember that's the way I usually teach it in Calc 1, like, what's the integral of x to the -1? It's like, I don't know, it falls apart. That's the weird one that becomes natural log of x. Anything else about this thing? How it works? All right. The integral of x squared e to the x. Here's something I want to do before we try to integrate this thing. Because the question came up, how do I know if I'm going to use integration by parts or integration by substitution? So let's talk about two functions. F of x equals x squared e to the x. And what's a similar looking one? G of x equals x e to the x squared. No, let's just do e to the x squared. For the function g, let's kind of like make a diagram for the way this function works. For function g, what's the first thing that like if we were going to like map out what happens to x to make g of x, what's the first thing I do to x there? Like if you square it, right? So the first thing that happens in this process is I square it, and the thing that comes out is x squared. Next step is to do what? So if you were going to put this in your calculator, I said, what's g of 5? First thing you would do is square 5, right? Then what would you do? Yeah, so raise e to whatever you got, right? So e to that, and that comes out to be ex squared. So that's g, right? Why am I doing this? You'll see. Let's do the same thing with f. In function f, what's the first thing that happens to f when I do that? Square it, right? So first thing I do is I square it. Then what?
You get X squared,
Oh yeah, so what comes out of there is x squared.
and then you multiply it. Oh, no. Is it over E? Oh, X over E?
You multiply by.
But so do I raise e to the x squared or just e to the x?
Yeah.
So really what I have here is I have these parallel things going on. So what comes out of here is e to the x, right? And then these things get joined together. Through multiplication to give you x squared e to the x. If I write it out like that, is it more clear that a composite function is only happening in one of those two things? Here's where I really like that the chain rule has the name chain rule. Because when you do it out, when you kind of break it down like this, only one of those really looks like a chain, like a serial step-by-step process for that function.
So for the, like, if we get a problem that looks like the second one, we're supposed to do integration by part.
That's what I'm getting at,
Oh,
is that really what I'm getting at here is what's the difference between a function that is a composite of two smaller functions, and what does a function look like that's a product of two other functions? If you think about the kind of things you have to do to x to process them to become the output, hopefully that makes it more clear what you're looking at. So all that to ask now, what process should I use to integrate x squared e to the x? Integration by parts. Also, that's the whole point of the section. So, don't need G anymore. All right, so I've written this down by myself a couple of times. Now I'll ask you. How do we do integration by parts? What does it look like?
U, V, minus,
Okay,
integral V dV
there you go.
equals UV minus integral V dV.
Okay. So now we have some decisions to make, or really one decision to make. What should our U be? X squared? Why? I'm not disagreeing, I'm just asking why we made that choice. Heard mumbles again.
Easier to integrate E of X.
It's easier to integrate e of x. Okay. Can you find a derivative and an integral of x squared? Can you take a derivative and integrate e to the x? Okay, so I think all of that is doable. There's another big reason why I think putting x squared as u is a really good place to start. When we do this process, maybe I need to go back and look at our first example. We kind of visited it here. Why did we make the decision to call u x and dv sine of x? Du become like differentiating x gave you something simpler to look at, right? So will that also be true for x squared? So I think it's a good place to start. We'll find out if it did not make our lives easier. So if u is equal to x squared, what's the consequence of that? Oh, sorry, dv is equal to the x dx. And then what?
And du is 2x.
2x dx. And what's v? E to the x. So now I can use that to re-express this. So what does this integral equal? X squared e to the x minus all right. We all agree that that's where we ended up. Did we do okay? Did we do okay with our choice of u and dv? Can we do the integral 2x e to the x?
You can do it again.
Do what again?
Integrate by-
You can. Do we have to? Yeah, we sort of do. So here's the bad news of integration by parts. There's no rule that once is going to be enough. So I will tell you we're on the right track. We just got to run through it again. So
Was you thinking if it was e to the x to x dx?
so if I wrote it with these terms reversed,
Yeah,
are you asking if it's okay to write it that way?
Yeah.
Yeah, it's fine to write it that way. Yeah. And if you have things multiplied by each other, then their order is pretty irrelevant. Okay. So marking this because we're going to come back to it. But now the integral I want to deal with is this thing. 2x e to the x dx. So what choices do we have to make here? Same start. What should u be this time? What was that? 2x. So remember we chose x squared because we were hoping it would get simpler. We saw that it did, we just couldn't get to the finish line in one step that way. So if u is equal to 2x, what else must be true? dv is e to the x dx. And we already talked about what v is when that happens. All right, what else? du is 2dx. All right, so knowing all those things, I can do this integral, which is what?
2x e to the x.
2x e to the x. Go on. Right. Okay. Do we have to do integration by parts again? No. Now we're good. So 2x e to the x, and what does this integral come out to be? 2 to the x. Are we done now? No, what must we do? What's that? Yeah, so now we can essentially. Are you okay if I no, let's not do the lazy thing. So I'll copy this down. So this integral becomes x squared e to the x dx equals x squared e to the x minus the thing we just got, which is 2x e to the x minus 2 e to the x plus c. We've come this far. Let's go ahead and distribute the negative sign. How are we doing with that? Ask me the questions. I'm sure you have them. Or have we mastered this? Go ahead.
So in a situation, you have like, e to the x and then like sine x or cosine x,
Mhm.
would it just not always repeat over and over again?
I'm so glad you asked. What would happen hypothetically? It's a good question. Because in this one of those gets simpler if you differentiate it, right? What happens with e to the x if you differentiate it as many times as you want? It is its own rate of change. It's infinitely differentiable that way. Absolutely, sorry.
Would it be, so why don't the negative sign distribute to the plus three?
Well, I left it out of the brackets. Here's the thing we kind of do with the arbitrary constant in integration. We don't know what it is, right? Nor will we ever know what it is. So subtracting something mysterious and adding something mysterious are basically the same thing.
Okay.
So it's very hand wavy, but we kind of play fast and loose with that C because we have no real way to like nail it down.
But for that one, like how we have that first integration we did, like the first one, right?
Mhm.
And then we did that second part, we did it again, and that gave us a plus C.
Yeah.
It wouldn't be 2 plus C.
So let's talk about that. It's a really good point. And I'll admit that I took a shortcut. By the way, when you do two integrals, there's no reason to believe those constants are going to be the same, right? So I'll call them C1. And I'll call the other one C2. And that means that this thing is going to be plus C1 plus C2. What is C1? No idea, right? What is C2? We know they're constants, right? What do you get when you add two constants together? A constant. So really, I'm going to scoop up all these things that I don't really care about, but I know that when I add them all together, they're going to be a constant. So that's why I know. So here's what I did. I knew that was going to happen, so I didn't really worry about the constants that were going to crop up in the middle steps. But even if you carry them all the way to the end, you're just going to kind of consolidate all. Another thing that might be a little more relatable to you, when you do a definite integral, you ignore the constant, right? Usually. Like, let's do a quick one. If I did the integral from 1 to 5 of x, let's do one even simpler, of 2 dx, that should be 2x plus c, right? From 5 to 1, but that becomes 2 times 5 plus c minus 2 times 1 plus c, right? What happens to the constant? Right, so we know it's gonna get annihilated, so we sort of ignore it early on because we know it's not gonna make a difference. The constant is simultaneously one of those things that we say must be there because it exists, but we treat it kind of, I don't know, neglectfully. Is that too harsh of a word? All right. So what happens when you have things that don't really simplify when you differentiate them? So when you differentiate e to the x over and over again, it stays e to the x as many times as you want to differentiate it. What happens to sine of x? Yeah, so it's cyclic, right? Every fourth derivative of sine of x is sine of x. So can we even do integration by parts on this thing? We must be able to if I'm asking you about it. So what do we need to choose? What's u equal to? Sure, e to the x sounds great. Which means dv is equal to sine of x dx. What's du equal to? E to the x dx. And v is equal to? Some flavor of cosine? Negative? Yeah. Negative cosine x. All right, so let's try this map and see if it works for us. So the integral of e to the x sine of x is equal to what? Negative e to the x cosine x.
Right. Integral on negative. Is that x equal sign?
Negative e to the x cosine x. What was that symbol? All right, these cancel out. Do we think we went the right direction? Is it clear at all that, do we think this is a dead end? Do we think we're on the right track? Is there any way to know?
Over and over again.
Well, I mean, if we can keep doing over and over again and never get, I mean, we can keep doing integration by parts, but if it never gets us toward the end, I don't want to do that. So I'll ask you to believe me that this will work. But knowing that it will work, what must we do? Second time. So I'm going to put a pin in this thing. Now we're going to integrate e to the x cosine x dx. What do you like for u this time? You want to use cosine x this time?
Sure.
What's dv then? Right, which means v is equal to e to the x. And what is du? Negative sine x dx. All right, which means that this integral now is equal to what? E to the x cosine x minus the integral of negative e to the x sine of x dx. And again, the negatives cancel. How are we doing?
Pretty much the same thing.
It's the same thing, right?
Oh, but
Do you notice anything?
yeah, plug in.
Here's a concern that I have is that I can plug in, but what do I have? I have the integral of e to the x sine of x dx equals negative e to the x cosine x plus this integral, right? Which is now the latest thing we did. Here's something I've never seen because I've never had a class do it the way you did it. Is this thing I just wrote down true?
Yeah.
It is. Is it useful?
No.
Not really. Everything's going to cancel out, right? The e to the x cosine x's will wipe each other out, and then if I could subtract the one integral to the other side, that is going to annihilate the other one. So I think we need to do this. What we did was correct and useful, or sorry, it was correct, wasn't useful. So that means that we need to rethink our whole u and v scheme. So knowing that what we tried before didn't work, what should we try this time? U can be equal to e to the x, which means du is equal to e to the x dx. So what's dv equal to then? Cosine x dx, which means v is sine of x. All right, so hopefully this gives us something more useful. The integral of e to the x cosine x dx is then what?
X sine of x.
E to the x sine of x. Good. Go on.
Plus
Actually,
sine of x, or minus, sorry.
you're
minus
good.
Sine of x. E dx dx.
Right. So minus the integral of e to this x sine of x dx. All right. So this looks different, right? So let's just try to drop it in and see if that, bears any more fruit. So e to the x sine of x dx equals negative e to the x cosine of x plus the integral we just got, which is e to the x sine of x minus the integral of e to the x sine of x dx. Is this true and correct? I don't think I made any errors. If I did point them out, it happens. I think it's true. Is it useful this time? I got a shake of the head for no, it's not. So let's go back to the starting point. What are we trying to figure out? What was the thing I initially asked you?
What's the inability to the X?
Yeah, I want to integrate that function e to the x sine of x, right? So essentially, it's kind of a weird way to think about integrals, but I think we can do it with what we have. Right, this time you can add them together, they will not cancel each other out. So I'm going to add through by the integral of e to the x sine of x dx. And what happens there? They don't cancel out.
You have two integral.
Because on the left side of the equation, it's positive, on the right side, it's negative. So adding them together doubles it. So 2 times the integral of e to the x sine dx is equal to negative e to the x cosine x plus e to the x sine of x. Very close. So remember, the integral I wanted was the integral of e to the x sine of x. We're almost there. What's the only thing that has to happen now? Divide through by 2. Running out of room. Forgive the ugliness. Come on, marker. So I've heard this technique referred to as a wraparound before, because basically you're not really, the way we got to the end of the integral is much different from the way we got to the end of this. Eventually you're gonna get to a point where just through like the cyclic nature of some of these derivatives, you're gonna wind up with the same integral as the one you started with. And then they stack up and you can solve for it that way. But again, doing integration by parts more than once might be necessary. Like, for example, I could very conceivably do this. That's a thing that integration by parts can do. I don't feel like making you do it, but it exists. Any questions? So we did a few of these, did 4 different examples, integration by parts, saw a few different flavors of how it works. We happy with them? All right. I don't want to start anything new in the next 2 minutes.
I don't know, good question.
Yeah, go for it.
For like problems that are similar to this one, but like are a little more complicated. And you don't see it immediately, like when to stop keeping integrating and
Yeah.
again, what would you recommend people like
So,
plug in and see what it
Here's the thing, like, we got pretty far on the second part, before we realized it was just gonna all die, right?
Yeah.
And I meant to say this, maybe I didn't know this was gonna happen, because I've never tried to like, because you guys kind of switched tactics mid-screen. I didn't know that wouldn't work, because I've never tried to do it that way. But this sounds like a cop-out answer, but the real way to know that this is not gonna work is if like it just stops like giving you useful things. For example, let's go back to the very first thing we did. If we made the opposite choices for u and dv here, then you're gonna get the derivative of e to the x, which doesn't get any more complicated, which maybe not scary, that probably won't scare you off. But if you make x squared dx your expression for dv, then you're gonna wind up with an x cubed term. That should set off bells that this is getting me further away from the thing I need to get to. Like
our goal is to make it simpler.
usually your goal is to make it simpler, like, but what the one we just did, there's no way to do that. You just kind of have to appeal to the fact that the derivatives of the trig functions of sine and cosine are cyclical. They repeat. But very, very typically, it's you're looking to drive simplicity out of this process. It's a good question. What else? Okay, I'll stick around for a little bit. Oh, I want to let you know the MCC. Don't you ever go there? It's the MCC, the Math Community Center. It's in this building, room 303, pretty much directly above us. That's where I'll be holding my office hours. I think it's the best kept secret of this department. So there are a lot of, and I say this especially for you, most of your engineering majors, but I think certainly, I don't think this is anybody in here's last math class. There's a lot of tutoring centers on campus, but once you kind of get beyond Calc 2, you start running out of people who can help you. In the Math Community Center, everybody who works there, including me, is a PhD student in one of the 4 math disciplines, which means we've all, even to apply to the grad school here, you have to take 371 and 343, which means we've all learned how to prove, we've all taken all the calc classes. Literally anybody in there who works there can help you. So I think as you kind of mature and get further in your math journey, that's going to be a place that I recommend you lean on heavily. So my office hours will be in there. It opens on the day after Labor Day. I don't know my hours yet, but I will by the end of the week. But when it opens, I think that's going to be a really good resource for y'all. Cool.
Where's it?
Directly upstairs. So next door to us right here is room 103. So directly 2 floors above that. It's pretty easy to find, thankfully. I know these doors they don't make any sense the way they're numbered.
The big classroom that's like, it's like outside and then that classroom that's there, or is it?
It's not yeah, it's not really set up like a classroom, but it's pretty big.
Like the one that's like closed?
Yeah. Mhm.
Oh,
So I feel like the rooms on this floor are numbered very strangely, but the good news is they're the same nonsense is going on upstairs. The same weird numbers or scheme is happening up there. But I'll give you more details when I have them. Otherwise, have a good day and we'll talk Friday.